Well, good afternoon, everyone. It's a pleasure to introduce Dr. David Mitlin, who's a professor in the Department of Chemical and Materials Engineering at the University of Alberta and the principal research officer of the National Institute of Nanotechnology at the National Research Council. Dr. Mitlin was born in St. Petersburg, Russia, and he received his doctorate in materials science received his doctorate in materials science at the University of UC Berkeley in 2000. Prior to joining the University of Alberta in 2004, Dr. Mitlin was at Los Alamos National Laboratory, where he was awarded a director's-funded postdoctoral fellowship. Prior to 2002, he worked at IBM Semiconductor Research and Development Center in Hopewell Junction, New York. His core expertise lies in synthesis, microstructure, and property relationships of nanocomposites and thin films, and in materials characterization via transition electron microscopy. His current activity is focused on the development of advanced nanomaterials for a variety of energy-related applications, such as oxygen reduction reaction or electrodes, electrochemical supercapacitors, lithium-ion batteries, and metal hydrides. Dr. Mitlin has published over 90 peer-reviewed journal articles, holds a U.S. patent, is an editor for Journal of Materials Science, and serves on the board of review for metallurgical and materials transactions. The title of his talk today is, well, actually he's going to give two talks today, the first of which is new positive and negative, or the second of which is new positive and negative nanomaterials architectures of supercapacitor electrodes, and the first of which is highly corrosion resistant platinum niobium oxide carbon nanotube electrodes for the oxygen reduction in PEM fuel cells.
Thank you very much.
Thanks very much.
Yeah, so our potential stat broke last week, so I don't have any results for supercapacitors to present. So I'm good. No, I figured I have an hour to talk, so I will ramble on about fuel cell OR electrodes, then lithium-ion battery anodes, and finally what presumably people came to see, which are supercapacitor electrodes. So the first work is actually, and they're all quite interrelated. There's a certain theme that runs through our research in terms of really tuning and tweaking and tailoring the microstructures to get, in some cases, remarkably improved performance, and in other cases, a little bit of humble pie and a lot of learning of why things don't necessarily work how you predict they would. So this is some work that we did, and actually still ongoing, with what is formerly NRC Institute for Fuel Cell Innovation, which is now NRC Vancouver, and Department of Simon Fraser, Michael Eicherling's group at SFU. So just a bit of a background for, this slide tends to go over a lot better when I'm presenting in places like Boston or California, where people are like, oh, Alberta, where's that? But we're still further north than you are, just to point that out, and actually quite significantly. So we're about 150 miles south, obviously not the same longitude as Alaska. Or, drive to the Montana border, go 500 miles south, and you're there. Alberta is known for its amazing national parks like Jasper and Banff, which is arguably the reason why I came out there in the first place. And it's also known for the second largest mall in North America, which is West Edmonton Mall. And having two young kids, you tend to see infinitely more of this than you do of this, because they don't climb very well at 5 and 3. And this is my institute. It's a smallish building on the University of Alberta campus, and it's connected to the chemical engineering and the mechanical engineering building via these pedways, because it gets pretty cold in 8 months out of the 12 during the year. So if you look at the CO2 potential for fuel cell, in my opinion, and I think it's a pretty, it's a reasonably well-educated opinion, essentially they're on par with batteries in terms of the net reduction in CO2 emission. Of course, a lot of it depends on where you're either getting your energy from, in the case of batteries, or where you're getting your hydrogen from. But essentially you get a pretty significant reduction in CO2 when you go from internal combustion engine to fuel cells. And of course, there's the other very obvious visible benefits like reduction in urban pollution if you're driving fuel cell powered vehicles. This is actually a straight AFCC slide. They put this on their website, so there's nothing proprietary here. According to them, fuel cell performance, and again, this is, you wonder how much of this is, I wouldn't call it marketing, but I wonder how optimistic this is. But the performance is an absolute green thumbs up. Safety is a thumbs up. Whatever comfort means for a fuel cell, presumably that means that it's small enough where you could actually build a car around it, is a thumbs up. Free start fuel cells do actually much better than lithium-ion batteries. Range is okay. They argue their reliability is pretty good. I think there's still a ways to go, and there's a lot of ongoing research, including this work, where reliability is a major issue. Longevity, which is fairly synonymous. Weight reduction, and the big area, which actually I'm not going to talk about, is reduction of costs, i.e. really getting the platinum mass loading down. So really, as far as this presentation goes, we're primarily focused on reliability, assuming the performance can be kept the same as existing materials, which is, again, you really argue want to improve both reliability and performance. So we're starting with a fairly good assumption that PEM fuel cells, which are near commercial technology for automotive applications, need improvement in durability. And a major unresolved challenge is specifically the durability of the cathode. If you look at an operating cathode, especially during start-stop type of operation, you get loss as high as 50% over, let's say, 10,000 cycles of your electrochemical active surface area. And at lower temperatures, this is, people argue, straight up dissolution of the platinum. And of course, that leads not only to the loss of electrochemical surface area, but also to reprecipitation of your platinum in your membrane, which is not that good. At higher temperatures and at higher potentials than 0.9 volts, you actually have rapid corrosion of the underlying carbon in addition to dissolution of the platinum. So you really have both effects. And what we felt was ingenious solution to this, which somehow didn't turn out to be commercializable, is Radoslav Odzich's group at, I believe it's Argonne or Brookhaven, basically took a bunch of niobium oxide, either synthesized via sol gel or via powder processing, so these real nanoparticles, and it's actually reduced niobium pentoxide. And they coated them with monolayers of platinum, which then de-alloyed to about 4 to 5, or de-wet to about 4 to 5 nanometer diameter crystals, mixed it with carbon black, and obtained remarkable activity enhancement. In addition to obtaining a remarkable activity enhancement relative to commercial platinum on carbon, the thing that we were really impressed by is that there was, I wouldn't say negligible, but very low reduction activity even after 30,000 cycles. So if you look at initial 30,000 cycles, your change in your over potential is fairly small. So this inspired us. This particular structure, for various reasons, A, it's been done, and B, it wasn't entirely, well, it wasn't commercializable. We tried something different. So rather than having the niobium oxide, then the platinum, then the carbon, we actually said, why not have the carbon, a very, very thin layer of niobium oxide, really sub-nanometer layer of niobium oxide, and then the platinum. So a bit of a different geometry. And what we did is we grew fairly, and this is, to us, this was to some extent a potentially commercializable method, because you could actually use decal transfer to take this architecture and put it in a real MEA. But also, it's kind of a general methodology for working with a variety of carbon-based materials. So carbon microspheres, carbon, various graphitic structures, micro rods, et cetera, microcones, nanocones. So what we did is we grew carbon nanotubes in a fairly coarse array on an Inconel support, really an Inconel thin film that was then either deposited on more Inconel or on bulk glassy carbon. And we either just, I'd say fairly routinely, sputtered deposited platinum on top of it, or we introduced a very thin layer of niobium oxide in between them. So niobium dioxide in between the platinum and the carbon nanotubes. So by geometry, the platinum layers were, the niobium oxide layers were 10 and 2 nanometers. And if you consider essentially the real surface area of this architecture is really about 12 to 14 times higher than the geometrical surface area. You effectively got about 1 and 0.2 nanometer niobium oxide films. And even if you're off by, let's say, 50% in your thickness estimate, that's still thin and really, really thin. So we had 3 different mass loadings of platinum, again, 15, 45, and 75 nanometer by geometrical area. We did standard RDE in perchloric acid solution, chloride-free counter electrode, measured the electrochemical surface area using hydrogen under potential deposition. So these are what kind of the as-grown carbon nanotubes look like. It was about 5% amorphous carbon and maybe 3% catalyst. So when we deposited the platinum on an Inconel support, we had this it's still really nano from, by definition of nano, since these are all less than 100 nanometers. But as far as we're concerned, we had this very, very coarse baseline structure of coarse platinum crystallites in the 001, the 111, and the 110 orientation. You can tell by the symmetry. So you have 4 111 planes here terminating at the surface. And when we deposited the same mass loading of platinum on the carbon nanotubes, as expected, even at high temperatures, the platinum really did not wet the carbon nanotubes well. So basically, here's the low mass loading, higher mass loading, and 0.15 milligrams of platinum on the carbon nanotubes. And especially, this is a spotted deposited, especially on the back side, you see a lot of isolated platinum crystallites. There's quite a bit of de-wetting. The sputter flux is coming in this way. And you would expect this because there's really no intermediate phases between platinum and carbon. There's negligible solubility at elevated temperatures and, of course, at room temperature. And really, platinum is reported to bond to defective and functional groups on the carbons, but it's still not, well, you could tell it's just not very good bonding between the two. So you have this kind of platinum architecture with coarse and fine crystallites sitting on the CNTs. And actually, you can image the platinum crystallites, and you can actually image the carbon nanotubes through the platinum. So when we grew the niobium oxide on the carbon nanotubes, the structure was fundamentally different. So niobium oxide wets carbon nanotubes quite well. So this is the thin and the thicker. So this is the 0.2 nanometer. This is the 1 nanometer layer of niobium oxide on the carbon nanotubes. You're seeing, these grains really resemble pancakes wrapped around, let's say, a drinking straw, around a water hose. So essentially, when you're imaging them, they look very large. They certainly look larger than 1 nanometer, but that's because you're imaging their maximum dimensions. They're actually quite thin, normal to their surface. And the wetting is almost complete. There's some little regions where you don't have niobium oxide wetting, but you could actually, again, see the carbon nanotube through the niobium oxide. And again, even with a thin layer, you had very good wetting of niobium oxide. And again, as you expect, because there's chemical interaction between niobium and the platinum. There's a strong chemical interaction even when it's an oxide. And then when you deposit the platinum on the niobium oxide, which actually is a classic textbook example of strong metal support interactions, platinum on a reduced niobium oxide, you have excellent wetting of the platinum metal on the niobium oxide. So the morphology looks fundamentally different with the exact same mass loading of the platinum that it did on the carbon nanotubes by themselves. So when we looked at the electrochemical performance, if you look at the kinetic activity, obviously the carbon nanotubes with the platinum will perform better than the platinum just on the Inconel, simply because there's more surface area. And you could see right away that the niobium oxide layer does ever so slightly degrade the performance, the OR performance. If you normalize everything by surface area, so if you look at the specific activities, actually the coarser platinum on the planar supports as expected does a lot better electrochemically than the platinum on the carbon nanotubes. But again, you still get pretty good performance, and you get a slight reduction activity with the introduction of the niobium oxide layer. If you look at the Kotaki-Levitch plots, you have 4-electron pathway. And if you look at the impedance spectra, the thicker niobium oxide gives you a significantly higher equivalent series resistance. So this is for 1 nanometer. But if you look at the 0.2 nanometer niobium oxide, your equivalent series resistance is not that different from just platinum on the carbon nanotubes. So essentially, there's a slight decrease in performance, but if you get the niobium oxide layer thin enough, the activity is on par with just platinum on carbon nanotubes. What we did, and this is one of the best quotes I heard in one of the fuel cell meetings that I went to, is when you're designing a new material, don't start out with something lousy and make it 50% better and go, oh, you know, we made great innovation, because you're just 50%, you know, it's 50% less lousy. So you have to have something that starts out being somewhat competitive with commercial catalysts before you can start improving it, before you can start saying anything about it. So what we did is we actually compared our platinum on carbon nanotubes and platinum with niobium oxide carbon nanotubes to commercially available electrocatalysts. So this is straight out of literature from various sources. And what we find is that our materials are, they're not on the high end of mass activity and specific activity, but they're on par. So they perform, I guess you could phrase like a mediocre commercial catalyst, which is not bad considering we never try to optimize it. It's actually a bit of a diffusion limited geometry because you still have a fairly thick nanotube forest. But essentially, it's very much in the range of what commercial systems behave like. And if you introduce niobium oxide, it's really about 20%, maybe 25% worse. But still, it's completely on par with optimized commercial electrocatalysts. And of course, what we found is that the platinum with the highest mass loading, we have the coarsest crystallites, and the thinnest niobium oxide layer gives you the best specific activity. So what we did now is we started looking at so the performance was, again, it's on par with commercial systems. It's not the best, but it's certainly not the worst. So then we started looking at corrosion stability. So again, for commercial catalysts, 10,000 cycles, you lose more than 50% of your electroactive area. This is platinum with amorphous carbon. If we look at platinum on carbon nanotubes, you lose in a reasonable voltage window, but not the most extreme. This is 0.6 to 1.1. You lose 8.4% electrochemical surface area, half-wave potential shifts by 17 millivolts, and your specific activity drops by 33%. If you introduce a thin niobium oxide layer, you essentially have a negligible decrease in the activity. So your electrochemical area loss is 1.6% versus 8.4. Half-wave potential shifts by 4 millivolts, and specific activity shifts 4.5% versus 33. So these are the CV curves. Never mind the green one, that's just the planar baseline. So the CV curves, the change in area tells you how much platinum you dissolve to first approximation. But you see the shift in the over potential for the platinum on carbon nanotubes and platinum on carbon nanotubes with niobium oxide. Okay, now this is where it got interesting. So then we decided to do the most aggressive voltage excursion in literature. So this is the DOE aggressive literature, aggressive test. It doesn't get more aggressive than that. You're actually really, you're pretty big voltage range, and this is something that completely destroys commercial electrocatalysts. This is meant to represent extreme operating conditions. So platinum on carbon nanotubes lost 47%. So it's still a little bit better than commercial systems, but you're in the same range in terms of loss. Half-wave potential shifts 65 millivolts, specific activity loss 66%. If you introduce a 0.2 nanometer layer of niobium oxide, you have a loss of 10% in electrochemical area, half-wave potential shifts of 8 millivolts, and specific activity only 10% loss. So to our knowledge, this was really the referees kind of agreed with us. This is probably the most corrosion-resistant electrode architecture for this class of nanomaterials reported in literature. And if we actually looked at what happens to the platinum during cycling, so this is platinum on Inconel planar. Notice you don't actually lose any surface area, but you dissolve all those nice crystallites. So you lose a lot of activity, but basically it's due to loss of these 100, 111, 110 type of facets. This is your platinum on carbon nanotubes. So completely, pardon the expression, completely nuked type of a microstructure. So lots of corrosion of the platinum, both from the front side and the back side, lots of corrosion of the carbon nanotubes. The platinum with niobium oxide, there's a bit of surface etching of the crystallites. These were taken at the exact orientation. So these are both from the front side. But essentially, the microstructure is intact. And your loss of activity is really due to loss of these coarser crystallite faces in your microstructure. But not only does niobium oxide keep the platinum from corroding, but it keeps the carbon nanotubes from corroding as well. So that's it. Summary, you could essentially read that yourself. If you want more information, it was came out recently in Energy and Environmental Science. Okay, next. Okay, I'm doing pretty good for time. So silicon wire, metal coaxial nanocomposites for lithium-ion battery anodes. So if you look at silicon as an anode material for lithium-ion batteries, it's by capacity, it's amazing. It's a wonderful anode material. And if you look at it by gravimetric capacity, and this is lithium 15 silicon 4, you actually don't reach the 4,500 capacity reported earlier by authors. So it gets, basically this is the terminal phase, lithium 15 silicon 4. The capacity is almost on par with metallic silicon, the gravimetric energy density. If you look at the volumetric energy density, this is kind of neat. It's actually significantly higher than that of lithium. So you have a huge capacity on the anode, and ideally, and of course silicon is cheap, so ideally this would be a great material to replace graphite and really to even compete with tin. But silicon expands 280% upon lithiation. Silicon is not a particularly ductile material. The 280% is for lithium 15 silicon 4. And of course, this gives you poor cycling stability. And there's been a variety of kind of fracture mechanisms that have been reported. And actually, as I'll show at the end of this talk, at least when you talk about nanomaterials, that's really not the mechanism that occurs. So, the people do all these wonderful calculations and show that, they cycle and you get cracks going through your material. But at the end, it's actually a bit of a, what's the right way to phrase it? It's a bit of a harsher failure mode than you would think, or that people have thought. So there have been a variety of approaches to trying to minimize this expansion issue, or at least try to work with it in terms of trying to get these things not to decrepitate during cycling. And people have used, again, bulk, it's a major problem. Nanoparticles, people have used have done a lot of work with that. Thin films, people have done a lot of work with that. Nanowires, people, at this point, have done a lot of work with it. So the advantage is you have large surface area for charge transfer and shorter distance for lithium diffusion. You eliminate binder if you're just growing these things on your electrode. That's kind of an artificial one because at the end you will have to achieve a high mass loading, so you'll have to have some binder. In theory, you have contribution of all the nanowires to the capacity. Again, you assume a good electrical continuity. And in theory, better accommodation of large volume changes without initiation of fracture. And there has been a good amount of modeling that shows that below about 200 nanometer diameter, these things should withstand expansion contraction better than conventional microparticles. The disadvantages is you have, again, large and anisotropic volume expansion. So whether it's a bulk, a nanoparticle, or a silicon nanowire, the expansion is the same in terms of percentage. And it's always anisotropic, and it always occurs. So if you don't want to, the only time you could prevent expansion is if you don't lithiate the material. If you want lithiation, you, by definition, get expansion. You also have, as I'll show, a very large surface area, and really significant loss of lithium due to SEI formation. So if you're running this material against a lithium counter electrode, and you have 95 coulombic efficiency, okay, no problem. It sounds like good efficiency. If you're running it against a lithium cobaltite cathode, after 20 cycles, you just ran out of lithium, right? So basically, you really need to address both the decrepitation and the SEI formation. And our idea, and it's not the only one, but I think we've done some fairly new work in this area, is could we use active, inactive, partially active, and partially active coatings to really improve these two aspects? So by active, I mean it fully lithiates, so aluminum goes to aluminum lithium, has 900 milliampere hours capacity. Aluminum oxide is inactive typically. Magnesium and magnesium silicide are partially active because they have a lot of kinetic constraints they basically lithiate sufficiently slowly that you don't really consider them too active of a material. So the first thing we did before we even got into thin films, coatings, is we started playing around with growing silicon nanowires. And there's different ways to do it. There's different methodologies reported in literature. And typically, you can't grow silicon nanowires on your standard copper anode backing. What you have to do is grow it on stainless steel, because when you grow silicon nanowires, copper would form silicides, and you would not have a real electrode afterwards. So people either grow them on stainless steel backing, or you sputter some kind of a barrier film and then grow the nanowires on the barrier film. So we did it both ways. We basically just grew them on very well-polished stainless steel electrodes, battery backing, or we grew them on a titanium nitride layer sputtered onto very well-polished stainless steel circular discs. And what we found is that it actually makes a profound difference. So the average diameter is about 100 nanometers in both cases. But here, you have these really coarse, these are really not even nanowires. These are fully microwires. You have some amorphous silicon. And equally important, you have very, very, very fine silicon nanowires. So if you look at the distribution, you have a lot of very small nanowires, and you have a lot of very large ones. It's a very spread distribution on stainless steel. On titanium nitride, it's quite uniform. So you have a fairly narrow distribution. So if you look at the capacity retention as a function of cycle number, the degradation is almost identical. But the initial capacity loss is here, it's about 5%. Here, it's about 15%. Actually, it's more than 15%. So you have a huge difference. I think this is maybe 17%. You have a huge difference in the initial capacity loss. And there's two reasons why this occurs. So first of all, these large nanowires, which hold a lot of lithium, it's been really shown, well documented in literature, that upon first lithiation, they literally just disintegrate. So they fracture. And the critical diameter seems to be, from calculations, about 200 nanometers. So the big nanowires that hold silicon disintegrate, so they stop after first lithiation, they're gone. And at the same time, you build up a lot more SEI layer relatively to the bulk lithium content in the really fine silicon nanowires versus the coarser ones. So when we looked at this microstructure, it's kind of a messy slide, but it really highlights things well. So you get these, again, microwires, very fine nanowires, and really this is first charge, discharge. Look how messy this looks. These big microwires are all entirely detached from the substrate. So you lose close to 17% capacity in cycle 1 simply due to catastrophic failure of the coarse particles and significantly more SEI layer formed. So now what we started doing is looking at the role of surface coatings. And we looked at aluminum, aluminum oxide, magnesium, and magnesium silicide layers. And these were spotted at 5, 10, 50, 100, 150 nanometers by geometrical thickness. The real surface area is 18 times the geometric, but the coating is not uniform. So don't take the numbers I'm going to quote as exact. This is sputtered deposition onto a non-vertically aligned array, right? So you're going to get a significant amount of shadowing, and you will, to some extent, penetrate near the base, but not entirely. We also played around with aluminum oxide deposited by ALD, which is a completely conformable process given our geometry, and we had 10 nanometers by geometric, so about a nanometer roughly, or maybe less, of aluminum oxide. So if you look at the cycling behavior, basically, so our baseline is the red, so 0 aluminum, and we do get, it's not a major, we're hoping for a major improvement, and we didn't get it, at least not with these coatings. We have some other ones that are submitted that we did get a major improvement. But in this case, we didn't really get, we got some improvement. It's, it's a pretty good improvement considering most things don't really help too much. But with a 5 nanometer by real area coating and 10 nanometer real area coating, you got a pretty reasonable improvement, especially towards the end of the cycling life of capacity retention. With the thinner coatings, you don't get much of an improvement. And with the thicker coatings, you actually don't get any improvement. So there's a certain sweet spot in terms of both capacity. If you look at the capacity retention, again, the 10 and I believe really the 50 are the ones where you get the best capacity retention. And thinner it doesn't work, at the 5 it doesn't work, and at the 150 and 100 it doesn't work. So it's kind of a sweet spot, not too thin, not too thick. And interestingly, your Coulombic efficiency, once you have significant onset of failure of nanowires, the remaining nanowires presumably don't form as much SCI layer or something happens, but your Coulombic efficiency actually starts to increase once your capacity begins to degrade. So if you look at the capacity retention with ALD, it's actually, initially it's a little bit better, but if you run out to 50 cycles, it's actually worse than with just pure nanowires without the aluminum coating. So the 5 and the 50 nanometer aluminum really seem to improve things, though not tremendously. And if you look at the nanowires, and this is kind of a classic, I wouldn't even call it a failure mode, but a classic cycling microstructural evolution of nanowires. So you start out with wires, and during cycling, they almost split. Like you take a pair of scissors and just chopping them in half and half and half lengthwise, so they kind of shred. And the post-cycle microstructure, this after 100 cycles, for the bare silicon nanowires looks like this. So it's kind of this, again, separated, very high SCI layer mess. If you have a thin coating, they seem to be more intact. If you have a thicker coating, so if you have a 10 nanometer coating, they seem to be quite intact. So compare this to this. Again, this coating unfortunately didn't penetrate all the way to the bottom. It's you have shattering, but essentially there's a very noticeable difference in the microstructures. And interestingly, the higher coating seems intact, but I'll actually show you that in fact it's not. Where you're looking at the aluminum and not really seeing the underlying silicon. So when you do the TM analysis, this is the bare. Actually, so this is the 5 nanometer, so this is the thin coating. Things, again, start to kind of separate. It's all amorphous in the dilithiated state. If you look at the 10 nanometer coating, the aluminum coating on the silicon is still intact. So you have your aluminum coating, you have your silicon coating. If you look at the interface, it's quite continuous. These are all, by the way, taken in the dilithiated state. It's virtually impossible to look at lithiated microstructures in a microscope without infinite number of precautions in terms of destroying the sample. If you look at the really thick coatings, what you see is really the wire underneath the silicon nanowire underneath the aluminum is not intact. It kind of disintegrates. And the aluminum stays, but the two are in fact separated. So when you try to image it, you actually see how you see the wire here? You actually don't see the wire in the thicker coatings. And in fact, what you see is the aluminum literally just kind of peels off the silicon. So if the coating is thick enough, they separate, and essentially it's ships passing in the night. The silicon nanowires behave like silicon nanowires, and the aluminum behaves like aluminum. So there's kind of an optimum coating where these things actually very much keep or to enough extent keep the nanowires intact. So the next two types of coatings we looked at were magnesium and magnesium silicide. And here we found absolutely no improvement in the performance, in the capacity retention. So 0 improvement in the capacity retention, literally negligible, nothing, but a pretty significant improvement in the Coulombic efficiency, which is, again, what I said before, it's a secondary but just as important issue is how do you keep from sucking up all the lithium in a real battery. And you have quite a boost in the Coulombic efficiency, especially when you're using pure magnesium coatings. And it actually doesn't really seem to matter how thick the coating is. So these are all, essentially it's the same curve, right? It's kind of a thickish curve. And here's the pure silicon nanowires by itself. And again, interesting, your Coulombic efficiency goes up once you start getting significant levels of failure happening. And what we did is when we actually did the XPS for the SCI layer, we noticed a pretty major difference. So in bare silicon nanowires, you get strong carbon-oxygen presence, really indicating you get your classic SCI product, which is polyethylene oxide on the coating material, which is an electrochemical process. So every time you form more polyethylene oxide, you consume electrons. If you coat it with magnesium, you form lithium fluoride, which is an electroless process, and you get an improvement in the Coulombic efficiency. So it's not necessarily that wonderful of a finding in terms of here's the solution, because A, the Coulombic efficiency is still not very good, and B, you're still sucking up lithium, but it really gives hints of how you can start playing around with different coatings to both improve the lifetime of the material and perhaps in a different type of a coating, change the structure of the SEI layer. Notice the silicon itself doesn't actually participate in the SEI layer formation. And why isn't there an improvement? Well, what we see, so this is your 100-cycled fib cross-section of the magnesium-coated silicon nanowires. And what you see is there's really no silicon nanowire left. It's just this giant agglomerated thin film clump of really silicon, magnesium, and SEI layer all interspersed with significantly enhanced levels of SEI layer formation near these type of voids, which were representative of the whole microstructure. So essentially, your failure mechanism is not exactly what people observed. It's not just fracturing of the silicon nanowires. In the case where you have a material that is, even here where you have reduced levels of SEI formation, but still some SEI formation, your failure mechanism is really this agglomeration and collective delamination of your silicon from your support. So this one is a lot tougher to fight against than just coating the nanowires with something and hoping they don't fracture. So in a sense, this kind of, while in the first case for the electrodes, there's a huge amount of hope just by introducing a very thin layer of niobium or various oxides between the platinum and the carbon. Here, I wouldn't say it's hopeless, but here's some limitations to how much you can improve silicon anode nanomaterials. So I'll let you read the conclusions. They're kind of self-explanatory. And finally, actually we're doing really well on time. Finally, hope I'm not talking too fast. Let me just get a drink. Finally, carbonized, and this is kind of this is a fun part that I don't know if there's more or less science, but it's kind of certainly fun to talk about. So carbonized chicken eggshell membranes with 3D architectures, flexible high-performance electrode materials for supercapacitors, and I'll also show some data for lithium-ion battery anodes, which should be coming out in Energy and Environmental Science fairly shortly. So if you look at supercapacitors, if you can, so this is your generic Ragone plot of specific power versus specific energy. And if you look where the supercapacitors fit in, they're kind of straddle the Netherland between capacitors and batteries. And really our premise, and it's not a particularly unique premise, but really what we're aiming for is that if you can keep the wonderfully improved power characteristics of a capacitor and make it perform like even a mediocre lithium-ion battery, you would enable a significant amount of new applications. So imagine a lousy lithium-ion battery, but that charges in 5 minutes for a laptop. There's some real potential markets, not only in the automotive, but also in consumer electronics and power tools, and I mean, you name it. If you're in Alberta, oil and gas. And the existing systems, and here's two representative commercially sold devices, are electrical double-layer caps based on activated carbon. So this is straight off the Maxwell website. Here's 6,700 watts per kilogram power and 3 watt-hours per kilogram device. So it's kind of straddling right the edge of the supercapacitor performance triangle. And here's one for heavy hybrid transportation, which is a 4,700 watts per kilogram device and 2.5 watt-hours per kilogram energy density. So these materials are actually fairly low energy density, reasonably high power, quite large, and interestingly are guaranteed to last for 1 million cycles. And they're made by electrical double layer, so no Faradaic reactions, of really high surface area activated carbons in a polymer electrolyte. So the pros is that it's stable over 1 million cycles, guaranteed. Activated carbons are relatively cheap. I actually looked up the price fairly randomly because it came up on my Google email for some reason. It's basically $2 a kilo for a good US manufactured activated carbon from coconut shells. But the con is that there's really a very hard limit to how much capacitance you could get, which is about 125 for polymer electrolyte farads per gram. And polymer electrolyte has actually significant toxicity, flammability, and well, really toxicity and really more so flammability issues in terms of these things are known to catch on fire. So all those problems that people have with lithium-ion, with laptop batteries before they went over to a lithium polymer battery, exist with polymer electrolyte. And an alternative approach, and again, I'm actually not here to debate which one is better, but an alternative approach is to combine electrical double layer capacitance with Faraday reactions to get much more farads per gram. And you have to do this in an aqueous-based system. So rather than using a polymer electrolyte, you basically just use KOH, which is quite benign. You don't even have to use an acid, you use a base. You literally could use 1 mole KOH. So this is our premise. So what if we could take carbons and really run a combination of electrical double layer and Faradaic reactions in an aqueous system and achieve on par energy densities? And what I'm going to talk about is really 2 topics. So the first part of the presentation, which is what was in the abstract, is for a very low surface area material with really very high nitrogen content, tuned surface functionality. And with that, you get quite high farads per gram. And this is the carbonized chicken eggshell membrane with 3D architectures. So here you have a bunch of chicken eggshells. And after you carbonize it, it looks like this really quite thin construction paper that's flexible. You could actually stack it. You could carbonize it to be thicker. And it's a very easy geometry to work with as far as supercapacitor electrodes goes. Because again, if you want to put this in a flexible device, it's quite easy. The next stuff, which actually we're quite excited about, is a fairly high surface area material with tuned surface functionality and now tuned porosity, and actually ultra high farads per gram. In fact, probably one of the highest ever reported, and certainly the highest battery reversible capacity reported for carbon in terms of milliampere hours per gram. And that's mesoporous nitrogen-rich carbons derived from egg whites. So if we talk about the eggshell membrane, there's really only 2 processes that we used. So we took this eggshell, removed the shell, have the membrane. We carbonized the membrane. And those CSM, so carbonized eggshell membrane, as prepared. Basically, the membrane was carbonized in argon at 800 degrees C, so not too much porosity, basically low surface area material. We then took this membrane and just activated it in air for 2 hours at 300 degrees C. And what we did is we got this, it's a very mild activation as far as, if you ever played around with carbons, 300 degrees C in air is it's considered very mild. And it's a short duration. So what we got is still a low surface area material, but on the outside, we're able to achieve significant levels of, or enough mesoporosity. So you have mesoporosity on the outside and kind of a monolithic, electrically conductive, nitrogen-rich core. So it's really very much a core shell structure. So you have good electrical conductivity, plus you have some additional surface area. And the 300 degrees C was low enough where you don't destroy the nitrogen functionality. And if you look at the macroscopic picture of this stuff, it's this porous kind of a interconnected foam which actually allows the chicken to breathe. So it has to be macroporous for things to diffuse in and out of the egg. And finally, we did a conventional KOH activation at 700 degrees for 2 hours, and we got something that almost completely resembles commercial activated carbon. I'll show you. It's in fact fairly boring. So this is the neat part. We're able to achieve, both in the as prepared and in the material activated at 300 degrees C, very high nitrogen content. So this is from elemental analysis. This is from XPS. And if you compare the two, you'll see that after the activation, your surface nitrogen content is a little bit lower on the surface than in the bulk, though not that much. And your oxygen is higher on the surface than in the bulk, as you would expect. And the nice thing about having your nitrogen in your bulk, in addition to your surface, is that during cycling, if you electrochemically dissolve some of the carbon, there's more nitrogen waiting in the bulk of your material. So it's kind of nitrogen all the way down. If you look at the activated eggshell membrane KOH, basically it's low nitrogen content. Again, it very much looks like a activated carbon. The surface areas in KOH was considered high surface area material, 1,500 meters squared per gram. CSM 300, still a very low surface area material, so 221 meters squared per gram. Most of it being microporosity, so 193 meters squared per gram. Let's say average pore diameter, very much in the microporous range. And this is interesting. Your electrical resistance was roughly twice as low as it is for a conventional activated carbon. So these carbons are nitrogen-rich, which give you a lot of Faradaic reactions, and they're actually quite electrically conductive. And they're not a powder. They're a connected monolith, so you don't really, or a porous monolith, so you don't actually need to even add binder. So you have an electrode with lots of nitrogen and very good electrical conductivity. So if we looked at the cycling performance, this is, we did both 3-electrode and 2-electrode testing. The CSM, as prepared, has this kind of an ion sieving looking triangular CV curve, but the material activating KOH and at 300 in air has box-like structure with very pronounced Faradaic peak. Especially if you look at the one in KOH, it's quite box-like. The one in 300, very, very nice pronounced Faradaic peaks. And people don't actually quite know what they are, but they're there, both on the reduction and the oxidation. We tested both in KOH and sulfuric acid. It worked quite well. If you look at the charge-discharge curve, very low IR drop, asymmetric because of the Faradaic reactions. If you look at the specific capacitance, this is a carbon. There's no oxide on here. It's not, it's just a low surface area carbon, 200 meters squared per gram. You have a capacitance in KOH as high as 300 farads per gram. And it drops, but even at a high current density of 20 amperes per gram, you have a capacitance of about 225 farads per gram. Cycling stability, remarkably stable. So again, in KOH, basically, well, in either one, you lose less than 2%. If you look at the equivalent series resistance, basically, you could just tell that as they activate at 300 degrees, the nitrogen-rich continuous electrode is much more conductive, as you expect, than the one that was activating KOH. And in 2-electrode, it still works. You get about 5 to 20% lower because you don't quite sample all the Faradaic peaks on both sides of the electrode. This is in a symmetrical configuration. And actually, we found the highest specific capacitance ever reported for carbon. So your theoretical EDL capacitance is 15 to 25 microfarads per centimeter squared. We got 120 microfarads per centimeter squared. So almost an order of magnitude higher specific capacitance because of the redox reactions on the surface. So next thing we did, and I'm not going to get too much into the synthesis process since this is technically still not published, though I hope, you hope to get the final acceptance letter sometime this week. But basically, so we took we actually synthesized mesoporous cellular foams, and we took the proteins, and there's some tricks here which I won't get into. I have a brilliant postdoc, by the way, that did this that clearly deserves a faculty position. He took the egg white, extracted the proteins, inserted them into these mesoporous cellular foams that he synthesized, carbonized the whole thing, dissolved the mesoporous cellular foam, and got this a two-modal microstructure where you have one set of pores that are 20 to 30 nanometers in diameter, corresponding to the diameter of these cells, and kind of this two-dimensional tubular porosity corresponding to the thickness of these foams, so basically 3 to 5 nanometers. So these carbons we called protein-derived mesoporous carbons, so PMC, we kind of got rid of the D. And all we did is just pyrolyze them in argon at 650 to 850 degrees C. So really PMC 650, PMC 750, PMC 850. And of course, at these temperatures, you lose some nitrogen, but these egg whites are so rich in nitrogen to begin with, I believe there's something like 50% nitrogen, that at the end you actually retain quite a bit. So especially PMC 650, you retain as much as 10% nitrogen. At higher temperatures, you lose more and more nitrogen. If you look at the structure, it's partially graphitic if you compare the G to the D bands in Raman. Macroscopically, it looks like, I call this caramel corn morphology, so it's popcorn that's interconnected. If you look at TM micrograph, you clearly see the large pores. You actually can't really see the small mesopores that are about 3 to 5 nanometers in diameter. We confirmed this. We got the surface area using both DFT and BGH methods, I believe. So you have a bimodal pore size distribution of a peak near 3 nanometers, another peak basically really should be about 20 to 30 nanometers, and it's a bit shifted because of how the modeling gets done. And it's quite high in nitrogen. And let's see, what else can I say about this high in nitrogen? The XPS, and we did elemental analysis, really gives you the same thing, that it's a bit richer in the bulk in nitrogen than it is on the surface, and a bit richer in oxygen on the surface than it is in the bulk. So when we looked at lithium-ion battery performance, so of course during cycle 1 we had fairly significant capacity loss, but during cycle 2, after cycle 2, which we got, I believe, 2,800, I'm sorry, we got 1780 milliampere hours per gram capacity. That's your reversible capacity after cycle 1. Stayed fairly stable. So you had a bit of a decrease, but basically this, you formed a lot of SCI layer. This is, the first discharge capacity is not meaningful. The second one is. So this is the CV curves. Your voltage profiles looks fairly similar to graphite. Your Coulombic efficiency is quite high after your cycle 1, of course. We actually, when we cycled it, we included commercial battery grade graphite as an electrode as a baseline, cycled at different current densities. Of course, at the higher current densities, it has less capacity, but this is you would expect that for any kind of a electrode material. But then you do the cycling and then go back to low current density, it actually springs back pretty close to the original value. And if you look at the cycling performance at 0.5 amperes per gram, basically you have fairly stable, well, it's just as stable as graphite in terms of capacity retention after 100 cycles. So this reversible capacity is quite high by literature values. When we looked at the Supercap performance, again, lots of nitrogen, lots of Faradaic peaks. So especially notice how as you go up in temperature, your Faradaic peaks get less and less on both the oxidation and the reduction. Charge-discharge, asymmetric, but low IR drop, good electrical conductivity. And here we actually got a specific capacitance as high as 400 farads per gram for the lowest activated sample, for the lowest carbonization. I'm sorry, the lowest carbonized sample. And if you cycle it again, you get less than 5% capacitance drop after 10,000 cycles. So we get 400 for a carbon without any, without any cobalt oxide on it, without any manganese oxide. So it's just from the intrinsic redox reactions of the nitrogen groups. So I think that's it. So thank you for your attention. This work kind of made the front piece of Advanced Energy Materials, made a few different websites. It actually made IEEE Spectrum this morning. And it was sponsored by Alberta Livestock and Meat Agency, or Taste Alberta, and Alberta Egg Farmers. And notice I don't have any oil sands. I don't have any tar sand sponsor, so please don't ask whether I get a check in the mail once a month from them. Because I don't. So we do, there are other things in Alberta besides big holes in the ground with tar in them. Thank you.
Thank you for that interesting talk. I was just wondering, how did you decide to use chicken eggshells as electrodes?
Creative.
Inspiration.
We're creative. I mean, I have a program on waste-derived value-added applications. So we've done things with paper pulp sludge. We've done things with cannabis casings. And this is if you look at, I mean, there's certainly a lot of creative. Xi came up with this. I strongly supported him. There was a lot of discussion about it. We tried it at work. We tried other things that didn't work. So it's kind of an evolution process. But at the end, it's a product that doesn't have a value-added application. It's something that gets thrown out. And there's two types. There's eggs for food, which in that case, you throw out the eggshell membrane. The eggshell itself, there's a machine in large industrial food processing plants, like a Twinkie factory, that literally separates the membrane from the eggshell. The eggshell goes back into fertilizer, into chicken feed, and into livestock feed. The eggshell membrane has a niche market for glucosamine, but beyond that, really just either gets incinerated or gets put into landfills. And they were looking for value added. For egg whites, we're not competing with any food sources because there's also a program in Alberta on using eggs for medicine to grow antibodies and for cosmetics. And there you use the egg yolk, and by law you cannot use any part of the egg for edible applications. So there, again, it's a value added of something that's normally a waste.
Linda?
So these membranes are really rich in nitrogen, is
Yes.
50% or something.
The egg white, we actually,
I'm talking about a membrane, which is
we
very
forgot to measure the, my guess is close to the same 50%.
But after you carry out the calcination or the treatment, they're
Just
about
50.
10% at the most. Maybe.
I'm sorry, it's 25, they're 25%,
So
25.
you end up with about 8%, 8 to 10% nitrogen.
Yeah, yeah.
So I'm a little puzzled at the capacity that you showed if you go back to the 1780 milliamp hours per gram.
Right. Oops.
I'm not-
Yeah, that's, I know what you're asking, and there's other mechanisms of charge storage as well. So if you look at this, actually I was in such a rush because I did 3 different presentations.
That's a pretty simple question, which is,
There's,
if you just, so if you go to the slide of the capacity, you're down, I think it's the next one or the one after.
Yeah.
No.
the lib capacity.
Sorry?
The lib
Yeah,
capacity.
this will be. So the one that, it's a little hard to see with the blue one, which is 450. We'll just use that one. But the slide, the capacity, this is capacity versus cycle number, bottom right-hand corner.
Bottom right-hand corner,
That one.
650.
450, 650.
650, yeah, yeah.
Okay, the blue one.
Yeah.
So you start off really high, you lose, well, almost half your capacity in the first cycle. So that's not really 1780. I mean, you've lost a lot.
Well, this is a different rate. This is a different rate.
1780 was some other rate.
It was a slow rate.
Okay, well, anyway.
It was a 0.1. Yeah.
My fundamental question is, we all know what the capacity of carbon is, which is about 370.
Well, that's assuming intercalation into graphitic
So
sheets.
if you take into account you have, say, 10% at the most nitrogen.
Right.
What would be that, what would capacity, if you assume that is all involved in some Faradaic process?
Okay,
what
at
would that
1780,
value?
we actually did that experiment because we burned off all the nitrogen and the surface area stayed the same. And you wind up with about 800 capacitance left, milliampere hours per gram.
Still back to my question.
So you have 1,000.
If you're assuming that 10% nitrogen,
Gives you 1,000 milliampere hours per gram.
what is that going to, what is the theoretical Faradaic capacity?
There is no, there is, I haven't seen, you may,
It's gotta
you,
come from somewhere.
right, but I haven't seen a very good theoretical explanation of where the redox reactions, both in supercapacitors and in lithium-ion batteries, what are the reactions involved with nitrogen groups? Like what is the binding between the lithium and the nitrogen groups? I haven't seen an explanation, so I haven't seen any listed theoretical values.
Well, what do you propose is the source of this?
Okay, so we have
No,
1,000.
you're not just plating lithium.
Well, I mean, you could tell that from the charging discharging curves, but also, okay, so
You're going pretty low.
right, but you don't, but I mean, you would get very, very specific things happening near 0 voltage, which we don't see.
It's pretty close.
We
I mean, I
don't,
don't see any Faradaic response in your,
I mean, what do you call
there's
this?
nothing that's sort of obvious in terms of.
Well, but I mean, this is all, I mean, this is not plating lithium. I mean, lithium plating would be near 0 volts.
Oh, that's pretty close. That's pretty.
That's 0.5, you already have significant, you're starting to get capacity from 0.5 to 0.
Well,
I mean, plating lithium is right at 0 volts.
That's my point.
Yeah.
And you could have an overpotential that's going to give you plating just because we're going a little fast.
We're not going fast, we're going very slowly.
Not to criticize the results. My
Right.
question really is not critical. It's where is this capacity coming
Oh,
from?
okay.
When we don't see any Faradaic responses.
Oh, well, okay, so there's a few things. The nitrogen groups, the binding between the nitrogen and lithium is not well understood. There's some kind of adsorption happens. It's kind of binding. I haven't seen a redox reaction listed. I haven't seen an intercalation reaction. I haven't seen a conversion reaction. I haven't seen a reaction that has nitrogen, in this particular case, carbon, a quinone group or some, a surface nitrogen group with a lithium having some kind of a product. I haven't seen that in literature. So it is known that nitrogen groups do store lithium ions and there's a redox reaction that happens, but I haven't seen an explanation. That's about 1,000 milliampere hours per gram in this material. The rest is from these other mechanisms in terms of intercalation, in terms of filling of pores, which I guess in some way you could view as plating, and in terms of surface absorption.
But if there's a specific redox reaction from lithium and that 10% nitrogen groups, you should see that electrochemically.
Well, but you see a sloping plateau. This is most carbons. You would need. If you had a separate phase, you'd have a more flattish plateau, but you probably don't have a separate.
I guess my point is that if there's some sort of reversible redox reaction that
Right.
involves the nitrogen, it should be evident in the electrochemistry, and at 10% nitrogen, it should be
Right.
pretty evident given the capacity that you have.
But I
You might
right.
want to look into the plating phenomenon.
We will for sure. I very very respectfully don't think there's plating happening because
But there has to be
especially.
an explanation.
This is not at 0 volts. This is, this capacity is at 0.5. That's not where you would expect plating to start happening. Plating you get right down here.
Anyway.
Okay, I very, very respectfully.
But I guess the
right,
question is then what is the mechanism? So
I think the answer is people don't
we
know.
need to find out.
People, the exact same question needs to be asked for supercapacitors, and again, I don't think people know.
Any other questions? Perhaps I can ask one. Obviously, niobium oxide wets carbon nanotubes and also platinum, but what motivated the selection of niobium oxide in the first place?
Well, originally we read out this just paper and said, okay, it's actually the most. You need a few things. You need an oxide that is electrically, at least a semiconductor. Can't be an insulator. So niobium pentoxide doesn't work, and we tried it. We actually now have another paper on it. So it can't be something that's too much of an insulator, and at the same time, it has to be stable within the voltage range. That really narrows it very, very quickly. According to other studies, the most stable material in this electrolyte is titanium dioxide, but it's not very electrically conductive unless you dope it or have it substoichiometric. The second most stable compound is niobium oxide.
Just sounds as if it would be a relatively expensive material. There's a lot of effort going into reducing the use of platinum, which is an expensive metal.
Right.
But niobium is also, reasonably expensive.
Yeah, but we're putting down 0.2 nanometers of it. The idea, where we could take this, you take, batch of powder, some kind of graphitic or even amorphous powder, okay, and you run it through an ALD system. Hopefully, you have it set up such that your ALD could work with powders, right? And all of a sudden, you coat it with a few monolayers of niobium oxide. You're paying for the precursor. The precursor lasts for, 100 kilos of this carbon black. Really, if you look at the costs of a fuel cell, not even of an electrode, but the fuel cell, I think either 80 or 90%, I forgot I think it also depends who you ask, but either 80 or 90% of it is the platinum. And you don't achieve economies of scale with platinum, right? It costs the same per ton as it does per pound.
Any other questions?
Research group might have questions.
I was wondering, for your silicon nanowire,
Yeah.
when the wires were amorphizing, I guess,
Mm-hmm.
did you come to a critical dimension or diameter where that didn't happen?
No, they always amorphize.
Always.
Well, you amorphize. It's actually fairly straightforward. You start with silicon nanowires. They lithiate. As they lithiate, they amorphize down to, I think, I think it's 0.2 volts above lithium plus. And then right at the end, you transform them to lithium 15 silicon 4, I believe, right? On the way up, you get a plateau as this lithium silicon intermetallic starts dissolving. So you get a two-phase region with that and an amorphous lithium-rich silicon, which then dissolves, you lose your plateau, and at the end you wind up with amorphous silicon. And there's no evidence that of small things not amorphizing or of big things not amorphizing.
So it's a matter of the amount of strain that you're introducing is a function of the size of the wires?
Well, again, you have a 280% mismatch, and this is all ambient, right? So once, silicon is easy to amorphize, right? And it's not gonna rearrange back at room temperature.
Here's my last comment.
Sure.
Most of your charge potential is, a lot is a pretty high potential. So I guess, sorry, I'm a little vague here. When I said that it was possibly plating, I didn't mean necessarily plating in the sense that you might think of sort of films of lithium, but more what sort of like hard carbon storage.
Oh, yeah, absolutely. I fully agree with you on that, yes.
And when you sort of packing lithium into some mysterious, house of cards type.
Yes, absolutely. Fully agree with you.
Going in as
Okay.
quasi-metallic lithium as opposed to, it's
Pore filling, yeah, absolutely agree with you.
yeah, and that's sort of an equivalent.
Yeah.
thing to-
Yeah, yes, okay, I'm sorry.
Sort of plating.
Because Jeff talks about plating as in like you're doing something wrong and it's,
Well,
yeah.
plating is, because if it's close to metallic lithium, then you might as well just be using metallic lithium by using carbon.
Right.
But a lot of your potential, a lot of your capacity, your charge capacity is a pretty high potential. And how do you explain that?
Well, I mean, you have a big hysteresis, right?
You have huge
Yeah.
hysteresis.
I mean, these
So
are,
that's kind of not very useful.
of course. I mean, again, we're jumping up and down about 95% Coulombic efficiency. 20 cycles, you're out of lithium in a real material.
It's just that if you have to go to 3 volts to get that
I mean,
charge back,
of course.
it's not.
I mean, we think there's actually some potentials in if you burn off the nitrogen. But again, I mean, Jeff has he has a very nice science review paper where he goes, these carbons are not going to work as real.
So they're kind of acting more, as I said, almost like hard carbons.
Yeah, for sure, absolutely.
If not, I'll ask you to join me in thanking Professor Mitlin for a very interesting talk and innovative use of eggs.
Thank you. Thanks.